students, so in this part we are going to study types of semiconductor. Basically there are two types of semiconductor, intrinsic as well as an extrinsic. Intrinsic are the pure form of semiconductor, whereas extrinsic are the impure form of the semiconductor. Extrinsic semiconductors are again divided into two, N-type and P-type. So all these type of semiconductor we will be going to study in this part. So let's proceed. Okay students, so now let's start types of semiconductor. So let me first tell you, there are in general two types of semiconductor. One is called as the intrinsic semiconductor and another one is called as the extrinsic semiconductor. Fine, so let's start with the intrinsic semiconductor. A semiconductor which in its extremely pure form is known as intrinsic semiconductor. Silicon and germanium are the most widely used intrinsic semiconductor, right? So basically a semiconductor in its a pure form, right? So what is the important term is here, pure form, right? So basically if we take the silicon material or germanium material, so they are a pure material, right? So they are categorized in terms of a intrinsic semiconductor. Now if we see the structure, let's suppose if we see the crystal structure of silicon. So the silicon structure in this silicon has the 4 valence electrons, right? So these dots represent silicon, right? So this silicon has, each silicon has a 4 electrons in its valence shell, and this shares, so they shares these electrons with the neighborhood silicon atom, right? So there is basically, we can say, the covalent bond is formed for every pair, right? So we can say that for a silicon structure, all the four valence electrons are covalent bonded, or we can say they are shared with the neighborhood silicon atom. Okay. Now see, both this silicon and germanium are tetravalent. That means each has 4 valence electrons in their outermost shell. So this is very important. So if we talk about the intrinsic semiconductor, they will have, so they will basically are the tetravalent in nature. That means they will have the 4 valence electrons in their outermost shell. Each atom shares its 4 valence electrons with its 4 immediate neighbors. Okay, so that each atom is involved in 4 covalent bonds. There will be a 4 covalent bond, okay, with respect to each atom, right? Now, so they are all bonded, okay, no any free electron is available for the conduction. Now when the temperature of an intrinsic semiconductor is increased, now see what happens when the temperature of the intrinsic semiconductor is increased. So if this now if you are increasing this temperature, and if this temperature goes on increasing and beyond room temperature, okay, so what will happen? The bond which they are bonded with, right? So the strength will go on decreasing, and at a particular temperature the bond will start breaking. So a large number of electron hole pairs are generated. See, when we are increasing the temperature, okay, and due to the increase in the temperature, when the electron hole pairs are generated, this process basically is called as the thermal agitation. Thermal agitation, that means the generation of electron hole pair due to the increase in the thermal energy or the temperature, we can say. Okay, now see, electron hole, so always there will be always electron and hole will be generated in a pair. There will not be any case like only electron is generated and only hole is generated. Now why? We will see this reason in the next slide. So since electron and hole pairs are generated, so electron concentration will always be equal to concentration of holes, and this will be equal to intrinsic carrier concentration. See, as I told you that so whenever the temperature will increase, or whenever the electron hole pair will be generated, so there will be always, they will be generated in the pairs. That means the concentration of free electrons will always be equal to the concentration of holes in that material, and that is called as a intrinsic carrier concentration, because this is a concentration, okay, of an intrinsic semiconductor. Therefore, it is termed as intrinsic carrier concentration. Now see, let's suppose if we take from this figure, due to the thermal energy, this bond breaks, and let's suppose the electron comes out and it becomes now free for the conduction. That means we can say that now see, whenever this electron and this bond breaks, right? So electron is now, we can assume, we can compare with the energy band diagram. So now this electron has shifted from the valence band to the conduction band. That means it was previously it was bonded. Now it has become free for the conduction. Now when it becomes free, it loses a vacant place at that previous place. So this vacancy is called as the hole, right? So therefore we can say electron and hole pair will be always be generated, okay, in a pair. So whenever electron goes from valence band to conduction band, so it leaves a vacancy called hole in the valence band. Now let's talk about extrinsic semiconductor. So this was all about intrinsic. Now what is extrinsic? So we have seen that in a pure semiconductor, that is in the intrinsic semiconductors, okay, they have negligible conductivity at room temperature. Now why? Because see, if we see at the room temperature, so almost all the electron valence electrons of the silicons are bonded with the neighborhood silicon atoms. That means we can say at the room temperature we do not have the free electrons with us for the conductivity. Now even if we increase the temperature, okay, due to the thermal agitation, there will be a formation of electron or hole pair, and there will be a few in number. Even if we apply an external voltage, okay, so the number of electron and holes pair will be generated, but again they will not be sufficient for a good conductivity. So to increase the conductivity of an intrinsic semiconductor, some impurity is added. Now what we are doing is, in a pure semiconductor we are adding up the impurity, and they are called as a doping, right? The impurity which are being added are called as a doping. This term is called as a doping, right? So the resulting semiconductor is called as an impure or extrinsic semiconductor. See, it's obvious, whenever we are mixing an impurity within a pure semiconductor or any pure, so that becomes impure, and we term here it as a impure or extrinsic semiconductor. Okay, now let's see the impurities which are added. Okay, so there is basically a certain range, okay, or the specific concentration in which we add the impurities. So they are added at the rate of around 1 atom per 10 raised to power 6 to 10 raised to power 10 semiconductor atoms. Semiconductor atoms we can normally assume as, if the semiconductor is a silicon semiconductor, so we are talking about the silicon atoms. If we are having a germanium material, so we are talking about the germanium atoms. So let's suppose if we are having a silicon material, so in there will be a number of silicon atoms in it. Now what we are doing is, we are adding up the impurity, okay, and the rate, okay, I mean the concentration we are adding is like 1 atom per 10 raised to power 6 to 10 raised to power 10. So like one impurity atom will be added per 10 raised to power 6 to 10 raised to power 10 silicon or germanium or any semiconductor atoms. Okay. Now the purpose of adding this impurity is to increase either the number of free electrons or holes in the semiconductor. Please pay attention here. We are either the number of free electrons or holes. See, the purpose is, we are adding up the impurity, and that impurity will basically act as a free electrons or free holes. So the impurity, so depending upon the type of impurity, so there can be a number of free electrons or number of free holes in a semiconductor. Fine. So basically there are two types of impurity added in a semiconductor, intrinsic semiconductor. Okay, so atom containing 5 valence electrons and atoms containing 3 valence electrons. See, we know that all the intrinsic semiconductor are tetravalent. That means they have 4 valence electrons in its outermost orbit, right? So if we are now the impurity which we will be adding, either it will have a 5 valence electron or a 3 valence electron. Okay, and the atoms which contains the 5 valence electrons are called as the pentavalent impurity atoms, and the atoms containing 3 valence electrons will be called as the trivalent impurity atoms. Okay, so example of pentavalent are like phosphorus, then arsenic, antimony, bismuth. So phosphorus, arsenic, antimony, bismuth, these are the example of the pentavalent impurity atoms. So they are called as the N-type semiconductor, right? So all the the semiconductor which made after adding up the impurity of pentavalent type, they will be called as the N-type. And if we are adding up the impurity that are like trivalent impurity atoms to an intrinsic semiconductor, so the extrinsic semiconductor will be called as the p-type semiconductor. And the examples of the impurity which are the trivalent are like aluminium, okay, gallium, boron, indium. Okay, so where we can see there are two types of semiconductor, extrinsic semiconductor. One is the N-type and another one is the p-type. So N-type semiconductors are basically semiconductors which has the pentavalent impurity atoms in the intrinsic semiconductor. And if we talk about the p-type semiconductor, so they are basically an extrinsic semiconductor having the trivalent impurity, okay, in the pure or intrinsic semiconductor. So first let's discuss about N-type semiconductor. So basically these semiconductors are obtained by introducing pentavalent impurity atoms and are known as N-type semiconductors. So the semiconductors in which we are adding up the pentavalent impurity atoms, they will be called as N-type. So example are already we have discussed phosphorus, arsenic, antimony, bismuth, and these elements have 5 electrons in their valence shell. Now out of which 4 electrons, see this impurity has the 5 electrons in its outermost shell. Okay, so out of these 5 valence electrons, the 4 electrons will form covalent bond with the neighboring silicon or any pure semiconductor, and the 5th electron will be available as a current carrier, right? So that will act as a current carrier. The impurity atom is thus known as a donor atom. So therefore this type of impurity atom, that is or I should say a pentavalent type of impurity atom, is called as or is known as a donor atom. Why donor? Because this pentavalent has 5 electrons, so 4 will be paired with the neighboring silicon atoms, and there will be one extra valence electron, and that is available for conduction, or we can say is available for donation. So it has one extra free electron left. Okay, so therefore this type of impurity atoms will be called as the donor atom. So in N-type semiconductors, current flows due to movement of electrons and holes, but majority are through electrons. Since we know that in a p-type there are majority, we are having a donor type, right? So they are having electrons as a majority carriers. Okay, so if we will increase, so we have added the pentavalent, so the number of electrons are more as compared to hole. So okay, even if we will increase the temperature, so the electron and hole pair will be generated, but even though the number of electrons in that material will be more than the holes, so we can say that the current will be majority through electrons, and thus electrons in a N-type semiconductors are known as the majority charge carriers, while holes as a minority charge carrier. Since electrons are more in number, so therefore they are called as the majority charge carriers, and holes are in comparatively less in number, so we can say that they are called or known as a minority charge carriers. Now let's see what are p-type semiconductor. Okay, so we have discussed n-type. Now p-type. So the semiconductors which are obtained by introducing trivalent impurity atom. Now see here. Now here we are adding trivalent, and in case of n-type we have added pentavalent. Okay, so the semiconductors obtained by introducing the trivalent impurity atoms are known as p-type semiconductors. Okay, so examples are gallium, indium, aluminium and boron. Okay, and these elements, since they are trivalent, so I mean they have the 3 electrons in their valence shell. Okay, now see, we are adding this impurity in a pure semiconductors which has the tetravalent in nature, right? So these 3 electrons, we are adding an impurity which has the 3 electrons in its valence shell. So these 3 electrons will be forming a covalent bond with the neighboring atoms, but still there will be a one vacant place. Okay, so let's suppose if we are adding, this is an impurity, this is an impurity, and let's suppose silicon is on its neighboring node, right? So now this silicon has the electrons, and the impurity has only 3 valence electrons. Okay, so there will be a formation of 3 covalent bond, but there will be a vacant place left here, and this we know that the vacancy vacancy of an electron is termed as a hole. So we can say the fourth covalent, due to the fourth covalent bond will remain incomplete, and therefore there will be a presence of hole in its structure. Okay, so this vacancy which exists, okay, in the incomplete covalent bond constitute a hole. So this vacancy will constitute a hole, and the impurity atom is known as an acceptor atom. Therefore these type of impurity atoms are known as an acceptor. Why? Because there is a vacancy, so it requires some electrons to be it requires electrons, okay, so that vacancy to be filled up. That means it will accept the atom. Therefore this type of impurity atoms are called as an acceptor impurity atom. So see, in p type the impurity atoms are called as the acceptor atom. In n type we say that the impurity are called as the donor, because they were having extra electron with them, but here we are having a deficiency of electrons, and due to that a vacancy is created, and that constitutes a hole, and therefore these are called as acceptor atoms. In p type semiconductor, current flows due to the movement of electrons and holes, but majority are through holes. See here the number of holes are more as compared to electron. Thus holes in a p-type semiconductor are known as the majority charge carrier, while electrons as minority charge carriers. So for p-type semiconductor, the majority charge carriers will be holes and the minority charge carriers will be electrons. While we have seen for the n-type semiconductor, in that case the majority charge carriers were electron and the minority charge carriers were the holes, right? Now let's solve an example and let's check how much we have gained till now. When impurities like trivalent or pentavalent are added in suitable amounts to a semiconductor, then so the question is, whenever we add any type of impurity, whether it is a trivalent or pentavalent, that means we are forming a semiconductor that can be either n-type or p-type, so it can be of any type, right? Then its resistance increases, its conductivity decreases, resistance has no effect, conductance increases. So these are the 4 options. So if we see first option, its resistance increases. This is not true, because the purpose, see, basically the question here asking what is the purpose of going from intrinsic to extrinsic. What is the need of an extrinsic semiconductor? This is what all question about. So in this question we have to see what are the advantage of extrinsic semiconductor over the intrinsic semiconductor. So option A says resistance increases. No, never, because we know that we have shifted from intrinsic to extrinsic just to increase the conductivity. We were having a negligible conductivity in an intrinsic, so to improve that conductivity we have shifted to the extrinsic one. So resistance increases is a wrong option. Its conductivity decreases. It's an opposite option, I should say. This is also not a correct answer. Resistance has no effect. This is also not appropriate or a correct answer. And so the correct answer is option D. Conductivity increases, right? And we have discussed. So when since we are adding impurity atoms, okay, either by trivalent or by pentavalent impurity atoms, so that impurity atoms helps us in increasing the conductivity of an intrinsic semiconductor. Increasing the conductivity of an extrinsic semiconductor over the intrinsic one. Okay, so therefore the option D is the correct answer for this question. Now let's solve this another example. So if N-type semiconductor is heated, then in the question we are asked that what happens when N-type semiconductor is heated. See, heated means basically we can say that we are increasing the temperature. That means that we are going for the process called thermal agitation. So we already discussed that whenever we apply a heat or temperature, then what happens is the bond breakage, right? So bonds are breakage. The covalent bond which are we can say that the electrons which are in the valence band, okay, they will be shifted to the conduction band whenever there will be an increase in the, or we can say in an appropriate amount of increase in the temperature. So if you see the option A, the option A says that the number of electrons increases and the number of holes decreases. This is not a correct answer, because we have already discussed that the electrons and holes are always generated in a pair. So there cannot be like the electrons will increase and holes will decrease. So there cannot be an inverse relation between electrons and holes. So whenever the temperature will increase, bond will breakage, right? So bond breakage will take place, and whenever the bond breaks, electrons generated and it leaves a vacancy, and that is constitutes a hole, right? So option A is not correct answer. The number of holes increases and the number of electrons decreases. This is also again a not correct. Option C, the number of electrons and holes both remains equal. Both remains equal. See, no, this is not possible. Whenever we are providing heat, right, so there will be a breakage of bond and the electrons and holes will be increased up. So option D is the correct answer. The number of both electrons and holes increases. So both will be increased in an equal proportion, right? Okay. So this was the example from this topic which we have covered till now. So students, in this part we have studied types of semiconductor. We have seen basically two types of a semiconductor, intrinsic and extrinsic. In the extrinsic form, there are again two types, p-type and n-type. We have seen that the n-type semiconductor are formed by doping pentavalent impurity atoms in the intrinsic semiconductor, whereas the p-type are formed by doping trivalent impurity atoms in the pure form of semiconductor. In the next part, we are going to study Fermi energy and the mass action law. So stay tuned with us.